So we continue with thermodynamics. We can divide the thermodynamics into two parts, thermodynamics 1 and thermodynamics 2. Thermodynamics 1 deals with the different aspects of introductory portion along with the first law of thermodynamics, and thermodynamics 2 deals with the second law of thermodynamics and related phenomena. Entropy, enthalpy, all these phenomena in the thermodynamics 2 portion. And thermodynamics 1 portion, it contains your first law of thermodynamics, work done, calculation and some related things. And there are a lot of thermodynamic functions actually. So these thermodynamic functions are mostly discussed in the second part, thermodynamics 2. Now what is thermodynamics first of all? It is thermo means heat and dynamics means mechanical work or mechanical work done or any type of that movement related activity. So heat and movement related activity, interrelationship between the two, that is the aspect of thermodynamics. Initially it was there, but afterwards thermodynamics aspect is extended a lot in different other fields of science and engineering. So thermodynamics is probably one of the most important subject for engineers. Okay, at least in my chemistry subject I can tell you thermodynamics is the most important one of the most important one that is required for engineers. So it is the relationship, interrelationship between the energy, conversion of energy, all aspects are there. Chemical energy into electrical energy, electrical to chemical, this all sorts of changes. That is obviously based on thermodynamic principles. So what is important, like we are using different type of motors, engines everywhere, the concept of thermodynamics is applied. The engines and motors, different type of mechanical instruments, whatever you are using, their thermodynamic principle is based on the thermodynamic principle. Heat work done, different type of work done calculation. Yesterday already we had some discussion about reversible work and irreversible work. So this work done, these are all principles based on thermodynamics. So different forms of energy, kinetic, movement, having motion, potential, suppose a body is kept at the high altitude, so that is supposed to be at higher potential, and if it is kept at the lower altitude, it is at the lower potential. So that type of concept is called potential energy. The difference of height itself is giving some energy difference, so that is potential energy. So we have the electrical potential difference. So in that case we are taking high voltage and low voltage. So that there is electromotive force, the plus side and minus side of the battery. So there is a current flow. So there is a potential difference. So that is also potential. Potential means some sort of energy storage. Now chemical energy, it is also storage, but in sorts of chemical form. So it can, if the chemical reaction is performed, then you are getting some energy, like we are burning some sulfur, we are getting some heat. That is a chemical reaction. So here chemical energy is converted to heat energy. Then you have thermal. Thermal energy is also very common form, and which is probably the most abundant form of energy, that is thermal. But it is most inefficient energy also. It is most abundant but most inefficient. If you burn coal, you are getting heat, but how much heat we can actually utilize? I am talking about thermal power plant. So you are burning tons of coal every day, but practically what is the efficiency? Do you have any idea? What is the efficiency of a thermal power plant, thermal power station? It is around 35-40%. So poor. So 60% is wastage, think over. Okay. It is so poor efficiency that only 38-40% maybe, but 60% or more is loss, great loss. If you burn 1 ton of coal, 60% of that ton of coal, the heat generated, is wasted. Why? Because whenever heat is generated, that is a natural tendency to get dissipated. So you cannot stop it. The dissipation cannot be stopped. Maybe you can control to some extent, cannot stop it. Whatever insulation you do, loss will be inevitable. It will happen. We are using bulb, for example. So we are using electricity that is giving us light. That is the purpose of bulb. But along with that, heat is generated. That is a loss. And whenever heat generated, that heat we cannot utilize also. Most of the time, a portion must be lost. A portion must be wasted. So that is the pros and cons of thermal. Thermal energy is very much diversified. Always thermal energy is generated everywhere, but always you cannot utilize it. Nuclear energy, by breaking the larger nuclear like polonium, thorium, uranium, this type of elements, we can go for fission or fusion of there is this fission, and if you take small element like hydrogen, there can be fusion. So by this fission and fusion mechanism, energy can be generated. That is nuclear energy. But the nuclear energy, there is a major problem. And what is that? Do you know? What is the major problem of nuclear energy? One is accidents. Whatever precaution you take, there is always a huge risk and hazard. Number two, the waste material generated, disposal of that waste material is a huge problem, very serious problem. Radioactive, not reactive, but where to dispose that radioactive material? Wherever you dispose, there will be problem. So you try different way. Number one option, you can put it into some steel trunk and put it under the ocean. Initially it was the normal procedure of disposal. But afterwards it was found even steel trunk cannot protect radiation. So radiation is going out and it is destroying the ecosystem there under the ocean. Under the ocean also there is a ecosystem, and we are destroying the ecosystem, and that ecosystem will also give some impact into our key chain mechanism. Or we have that different type of that chain, food chain. No? So food chain will be devastated if there is a radiation. So you cannot dispose under the ocean. Now second option, you can put it under the mine. That is abandoned mine. You have taken out coal, so lot of holes generated. You have taken out coal, so that means a lot of rooms are empty. So there you can keep it under the ground, maybe 200 meter depth, 300 meter depth, it is kept. Still, it is found that if there is an earthquake, it comes out and it is giving radiation throughout the environment. So it is giving a nuisance, very serious trouble for human. Then what other option? Third option, you can send it to space. But space is also, we are using space. Nowadays we are using space also. We have satellites in the space. So where do you dispose? Wherever you dispose, it will create nuisance. And it is very costly idea also. If you try to send it to space, really costly idea. Molecular energy, translation and rotational molecules have some energy contained in itself. That is called internal energy. Molecules are having some energy contained, that is called internal energy. What is that? Rotation, translational movement, vibrational movement, all these movement is giving some sort of energy. It is called molecular energy. Kinetic energy, potential energy, thermal heat energy, chemical energy, and already I have discussed. Okay, so I can go ahead. So there are pros and cons where you can use. Potential energy, one application I am telling you. What are there in the top of the maybe rooftop or into the huge tanker? Water is filled by a pump house. Very good example is pump house. You know pump house? There is a storage tank. Tank number 13, tank number 14, maybe you have heard or seen. So water is stored in enormous quantity. That water is at a high potential energy because it is at a higher altitude. If you allow the water to come down, it can rotate the turbine also because it will have a high potential, so that potential energy getting converted to electrical energy. That is possible. But the thing is, You have to send the water at the rooftop or at the top of the hill by pump. So you are spending more energy than you are utilizing. So no benefit. Do you actually know what is the importance of tidal power, the hydroelectricity? What is the main importance? Where do you utilize it? Because already I told you, whatever energy you are gaining by this tidal power, in this case, by pumping and at the rooftop and then allow it to come down, you are actually losing energy. Because you are using more energy to send the water at the top, and then you are getting lesser energy. So it is not beneficial, no? Spending more, getting less. So it is not beneficial. Then why people should do it? But people are doing. Why I am telling you? Suppose there is a scarcity of electricity in the daytime, when all the school, college, office, hospital, everything is on, open. There is a utilization, huge utilization. Then there is a scarcity of electricity. After the sunset in the evening, most of the school, college, office, hospitals are closed. Maybe some are open, but most of them are closed. So their consumption is minimized or stopped altogether. So consumption is less. So that particular problem we cannot solve by thermal. Thermal you cannot make it on and make it off. Thermal there is a problem. Thermal once you start, the unit will run long period of time. You cannot stop it in the middle. And if you stop it, charging again will be very serious problem. It's difficult. Making on and off is difficult. So what we do then? Let the electricity be generated. By using the electricity, we are pumping in the pumping station, sending the water at the top, some in the storage tank. Then in the daytime, allow the water to flow down, get the electricity. When the consumption is very high, we can produce some extra electricity that time. Though there is a loss, still there is no other way. There is no other option. And people are doing it. And normally the hydroelectricity we are generating by running water from the top of the mountain, hill area, Brahmaputra river. The water is coming down at the Bhutan, Sankosh Jal Bidyut Prokalpo. So these are the some really famous hydroelectricity plant. There we are using the natural energy, and that water is already at the mountain top, and that is flowing down in the form of streams, that fountain, different way the water is coming down. That water we are using to rotate the turbine and produce electricity. That is real hydroelectricity. But another process, what I told, that is human procedure, human method, because that thermal power plant, there is a limitation. Once you make it on, it will run for a very long time. You cannot make it on and off. So you can use in a different way by pumping the water at the top of some storage tank and then running the water down, so that you can get the electricity extra or additional electricity during high consumption period. Okay, got the idea? Molecular energy we cannot utilize. It is there. Molecular energy is not utilizable. Most of the time not utilizable. Maybe sometimes, normally not. Because molecules are always in a Brownian motion. Random movement, zigzag pattern sort of movement. And that energy is there. But that energy, until unless it is 0 Kelvin, energy will be always there. But you cannot utilize much. So that's why in the first law of thermodynamics itself, you learn that Q, the heat energy supplied to the system, will give some amount of energy, and some energy will be utilized to enhance the internal energy of the system. That means there is a loss. You are giving 100 kilocalorie of energy. Maybe you are getting 60 kilocalorie work. Equivalent to 60 kilocalorie, you are getting the work. Rest 40 kilocalorie is going to raise the internal energy of the system, which is useless. Because the internal energy of the system, if enhanced, what is your benefit or our benefit? Got it? So that is a loss. And first law of thermodynamics is telling that loss is inevitable. You cannot avoid it. Whenever you want to convert heat energy into some other form of energy, a portion of the heat will be always wasted. You cannot stop it. That is the law. First law of thermodynamics. What is the law? Formula Q equal to delta E plus W. Q means the amount of heat supplied from the surrounding to the system. That is Q. Out of that you are getting W amount of work by heat engine. Suppose that is a heat engine. W amount of work. Heat engine. What is a good example? Our IC engine. Internal combustion engine that we are using in the vehicles. That engine. So there we are supplying heat. That heat energy, how do you get? By burning fuel, by burning petrol, diesel, we are getting the energy, heat energy. That heat energy is running the engine, heat engine. But do you think it is fully utilized? Never. A portion is utilized and portion is a loss. And that's why your exhaust pipe is so hot. It is spoiled, that heat is going radiated everywhere. That's why the exhaust pipe is so hot. Car exhaust pipe or bike exhaust pipe, if you touch, your hand will be burned. So hot, na? So why? Because it is actually burning inside. That is called internal combustion. So combustion is going on, real combustion. But you cannot see the flame because it is contained inside the system. It is contained inside. That's why you cannot see. But the heat is coming out. So electrical energy, electrochemical energy, sound energy, all these sorts of energy we are utilizing some way or other. How we are using sound energy? Tell me. How we are using sound energy? Telephone, we are using sound, converted electricity, going to some other place, again converted to sound, then only you can talk. Telephone. Sound energy practically we are using. Sound energy can be used by conversion I am talking about. We are using by so many ways. Ultrasound, USG, ultrasonography, you know? USG you know, na? So that ultrasonography, USG, they are utilizing sound. But conversion of sound energy into electricity, best example is telephone. And electrical energy is the best energy because it is so sophisticated energy, you can use it anywhere, any form, and it is loss is minimum. But the electricity energy is costliest also. It is most costly. Okay, it is costliest, electrical energy. And which is the cheapest energy? Which one? Thermal, which is abundantly available but inefficient, very inefficient. 30-40% already told you, very much inefficient. But still, see our car, what we are using? Heat energy. Because there is no alternative. What alternative will be using? Battery. But how do you charge the battery? Again you are burning some fuel, burning coal and then charging the battery. Battery is same. How we are doing something good to nature? Again you are burning coal to charging the battery. What is the benefit? Okay, maybe it is much more portable system. You are making it a bit lighter vehicle. What else? You are not getting any benefit, real benefit in terms of that pollution. Okay, you read out afterwards. Huh? All these things I am not going to read for you. That is a very bad idea. Reading the, I am telling you, reading the PowerPoint. Never read PowerPoints. Let others read. You say whatever you need to say. Now, I already told you that heat energy is highly getting diffused. It is getting dissipated. Now, I was into Mejia thermal power station. Maybe you have heard Bankura Mejia thermal power station. I was visiting there and found there is a very good insulation. So many ways. First of all, the insulation packaging on the pipelines where the heat is, the steam is passing to the turbine. First of all, water is boiled into some boiler, right? So from the boiler, the steam is coming to the pipeline. That pipeline, the steam is going to turbine, rotating the turbine with the steam pressure, and then the turbine is connected to some dynamo, and that's why that is generating electricity. Very clear? And you know what is a dynamo? What is a dynamo? No idea? No, but why? But what is that? What is the cross section of it? What is there inside? It is a coil and one magnet. Magnet rotates inside the coil. There is a circular coil. Inside the circular coil, let it be a bar magnet. This is a bar magnet. Just rotate this bar magnet, whatever way you can. Rotate the bar magnet. So electricity will be generated. That is the way it is done. So, yeah. Transfer of energy by the movement of substance, different way. There are a lot of examples here and there, practical examples. System, whenever we confine our attention is the system. From the universe, energy or matter can be exchanged. If it is exchanged, then it is open. Only energy exchange, then close, not open. And neither energy nor matter is exchanged, then isolated. Open, close and isolated system. As I discussed yesterday, so I skip it here. Nuclear energy, how do you do? How do you get nuclear energy? By fission. And which one is used normally? Uranium-235 molecule is used, particularly. This nucleus is used for fission reaction. Uranium-235. And uranium-238 is not fissionable. Uranium-235 is fissionable. That's why you have to first separate out 235 from 238 and then undergo this fission reaction. Uranium-235 is fissionable and uranium-238 not fissionable. That's why you must to separate them. How do you separate them? Both are physically, their chemical and physical property very close. Chemical property is same, physical property very close. Then how do you separate? By effusion. You understand effusion? It is a principle throttling process. It is called throttling process. It is also a thermodynamic process called throttling process. You have uranium-235, uranium-238 mixture. Now allow it to pass through some porous surface. So 235 molecule will pass faster compared to 238 because 235 is lighter and 238 is heavier. So heavier one will be lagging behind and lighter one will be moving ahead faster. So that way separation is done. Throttling process. It is also called effusion. Effusion. It is a type of diffusion called effusion. That we are separating it and then it undergoes this fission. How? By bombarding with slow neutron. By bombarding with slow neutron. First neutron cannot break it because first neutron cannot transfer sufficient energy to the nucleus. You may think first should do it better. No, first is moving so fast like a bullet. It is not transferring sufficient energy to the nucleus. That's why the breaking is not done. But slow neutron can do the job. It is entering into the nucleus, then making the nucleus unstable. The vibration is more, then it breaks into two parts. Barium and krypton. So uranium is broken into barium and krypton. There are some extensive properties, extensive and intensive property. Extensive property mass independent and intensive property mass dependent. Different type of processes also I have discussed yesterday, so I skip and go ahead faster. Now this point I will have to discuss a bit because yesterday I have not discussed it. But this is called path function and state function. State function depends only on the state. For example, you have that H, this is the heat content. Before the reaction, the heat content, and after the reaction, the heat content. You are doing some chemical reaction. Before reaction and after reaction. Okay, let it be HA and HB. HA is the state for the state A and HB for the state B. So what is the difference? HB minus HA, that is called delta H. That is the amount of energy either released or absorbed in a reaction. If the energy is released, we call it exothermic process, and if the energy is absorbed, it is endothermic reaction. So these endothermic and exothermic reactions, they are also, we can call them endothermic and exothermic process, because reaction is also a process. Process can be anything. Process can be reaction, process can be melting of ice, physical process, chemical process. Okay? They are all processes. So state function, that is only depends on state. So you are burning some coal for converting carbon into carbon dioxide. Now it can be done in two different steps. One is C plus O2 giving you CO, then CO plus O2 giving you CO2. So we are doing in two steps. Or directly you can do C plus O2 equal to CO2. Both are possible. One is incomplete combustion followed by complete combustion. Other one directly complete combustion. Possible. If you give insufficient air, then incomplete combustion. Then allow it to expose to sufficient air, complete combustion. So it can be done in two steps. On the other hand, if you give sufficient your oxygen from the beginning, complete combustion will take place. So two different way we are doing. One is by two step and this by one step. So whatever way you do it, the amount of energy released due to burning of same amount of coal will be same. State function. Clear or not? So it is state function. Burning of same amount of coal, whether you go by pathway 1 or pathway 2, as the two different pathways I have told, the amount of energy released will be same. Whether you go by two steps or go by one step, the amount of energy released will be same. That is state function because it depends only on the state 1 and state 2. State 1 is carbon, state 2 is carbon dioxide. So you are getting same amount of energy. That is called state function. Path function, the work done. As I told you yesterday, work done. Reversible process. It is happening very slow and minute ways, always maintaining the equilibrium. You are getting some work done, and that work done is always higher. And if you go by irreversible process, where suddenly the mass that is kept on the top of the cylinder is suddenly removed. This I am talking about from the class. If you remember, there is a cylinder piston arrangement on the top. There is some weight, 1 kg weight. Just remove 1 kg weight, so suddenly the piston will move upward. So then this is a irreversible process, and the energy the work done will be less. But if you allow it to do in a very slow and minute way and maintaining equilibrium always, that is reversible process, then the work done will be more. Can you tell me why? How can you prove that work done reversible is more compared to irreversible? How do you prove? Can you prove the reversible work done is more compared to irreversible? Can you prove that? We know that, but can you prove that? There are different ways we can prove it. Number one way is called physical way. Think over. What are the two parameters they are involved? Pressure and volume. PdV, no? P delta V. Pressure and volume, two parameters are involved. Now in case of if you talk about the irreversible, then what is the work done you are getting? P2 into V2 is V1. P2 into V2 is V1. Achha. Now, and not only that, the P2 is always lower compared to P1. P2 is lower than P1. So, P2 into V2 is V1, the value will be less. But in case of reversible, the pressure against which the expansion is occurring is not P2, but P1 minus dP, P1 minus 2dP, P1 minus 3dP, and so on. Slowly the pressure is released and expansion is occurring. And always the expansion is occurring against a higher pressure. Think about that language, what I am telling. Okay? The expansion is always occurring against a higher pressure. So P part is higher and delta V is same. So what do you get? More work. But in case of irreversible, P2 into V1 is V1. P2 is less. So P2 delta V will be less. So work done irreversible will be higher. Another way, mathematically also you can prove P2 into V2 is V1 is less compared to integral PdV. That also mathematically can be proved. Third method, there is a graphical method. In the graphical method, as I remembered yesterday, I drew there is a curvature, and if you take the curvature, under the curvature, the total area under the curve, it is higher, and for irreversible, it was a rectangle. Remember, it is a rectangle. So it was less, but in case of reversible, it was a extended one. Your voice is coming. Be silent. It is getting recorded also. So first law of thermodynamics is what? It is the law of conservation of energy. First law of thermodynamics is nothing but the law of conservation of energy. It tells that energy can neither be created nor be destroyed. That you already know from childhood, isn't it? You already know from childhood that energy can neither be created nor be destroyed. But when we became grown up, we came to know that it is entirely not true. Mass energy interconversion is possible. So that's why total mass and energy is conserved, not separately energy, neither separately mass. Mass energy total is conserved. Okay? Now we believe that. Earlier there was a law that energy is not destructible, right? But now we know mass and energy interconversion is possible. So mass can be converted to energy, and what is the equation? E equal to mc square. Okay. So that is the first law. So this is mathematical formula of the first law of thermodynamics. Delta E plus W equal to Q. Already I told you. Verbally I told you. Now see this here. So Q equal to delta E plus W. By means by the system. Here by means by the system, to make it very clear. There should not be any confusion. So it is by the system. And if it is on the system, sign will be changed. That's why Q plus the W on. Work is done on the system. This is the thing you have to remember. If it is by the system, then Q equal to delta E plus W. If it is on the system, then delta E equal to Q plus W. That means sign of W getting changed. By the system and on the system, just opposite sign. Okay. Next. Positive Q, heat added to the system. Positive W, work done by system. This if you remember once. So heat added, it is going from system to surrounding, then Q will be negative. Surrounding to system, positive. So system to surrounding, negative. Work done by the system, if you take positive, then by on the system, negative. So expansion by the system. Expansion is considered by the system, and your contraction on the system. Accordingly, you get plus or minus sign. So that is the sign convention. You can go through any time. Okay, sign convention. Q positive, heat flow from surrounding to system is positive. So you remember one, na? That's enough. Surrounding to system is positive. What? System does work positive. So one you remember, other one will be automatic. Now internal energy, Q minus W, that is delta E, is the internal energy change. But the real internal energy cannot not measurable, but internal energy change is always measurable. We are getting the internal energy change. We are calculating the internal energy change. So Q equal to delta E plus W. So that delta E is actually E2 minus E1, final state minus initial state. So the changes we are measuring. Compression and expansion. Compression means on the system and expansion by the system. So here dq plus W and here it is minus. On the system, minus. That means compression is minus. On the system, compression is minus. When you are doing compression, that means you are working on the system, doing something. You are doing, system is not doing. And when expansion going on, system is doing. That we think. So there are some processes, your chemical and physical processes in the nature that is listed here. So, okay, so solar energy, photosynthesis, different type of processes that is happening here and there, everywhere. That some sort of energy change, conversion is going on. electrical energy to mechanical energy, mechanical to electrical, all sorts of energy changes that you have already learned from class 7-8 standard, the energy conversion, that is practically happening in nature, not always by man, not by mankind always, by nature itself. It is always happening. Photosynthesis is natural phenomena. There also the solar energy is converted to chemical energy. Solar into chemical. So windmill kinetic energy of air is used to produce electricity. Wind power, heating of water, these are all based on thermodynamic principle. These are all applications. Windmill, solar energy, different type of energy resources that we are utilizing based on thermodynamic principle. That is the application of thermodynamics. That's what I'm showing you. Chemical energy converted to heat energy in exothermic reaction, and for endothermic delta H is positive, and for exothermic delta H is negative. That you need to remember. Delta H is negative means energy is released for exothermic process, and for endothermic energy is absorbed. Endothermic reaction, exothermic reaction. Example, if you take some lime, put into water, exothermic reaction. Sulfuric acid, put into water, physical process, but still exothermic. Physical also can be exothermic, endothermic. Chemical also can be. Putting some sort of lime into water, that is chemical reaction. Because calcium oxide converted to hydroxide. So the chemical reaction, they are also heat generated. If you put some glucose or ammonium chloride into water, it becomes cold. It is cooled. Why? Jano keno hai? If you put some sugar, fine powdery sugar, or maybe glucose powder and mix into water, it becomes colder than earlier. The temperature is dropped. Have you seen that or not? Observe. জলে চিনি গুললে হবে। অবজার্ভ করেছো? ঠান্ডা হয়ে যায়। বলো কেন হয়? কেন বলে? ঠান্ডা তো হয়, কেন হয়? কোনো রিঅ্যাকশন হচ্ছে না। No reaction here. Physical. If you boil the water, the sugar you can get back, right? But then what is happening? That is becoming cold. That idea is you get from thermodynamics. See listen to me everyone and don't talk. Sugar or glucose or whatever, it is crystalline material. Now it is an ordered state. When you put a pinch of sugar or glucose into water and stir it with some spoon, then it breaks into very fine particles and dissipate into the interstitial spaces into the water. Dissolution means what? What is dissolution? In the interstitial spaces, the sugar molecule or glucose molecule getting separated from each other and going inside the interstitial spaces of the water molecule. Then what is happening? Each and every water molecule is getting connected to the sugar molecule by hydrogen bonding. Lot of hydrogen bonding is generated, that is producing some amount of some energy. But now there is another thing is happening. The big crystal lattice broken into fine powder, that will need lot of energy. Breaking anything will need energy, na? So a lump of sugar broken into very fine particle, it will also need lot of energy. That energy is collected from surrounding itself. That is number one. Number two, the entropy of the system is also enhanced. Entropy increased because it was ordered. Now it is getting disordered. Earlier it was ordered, a sugar lump, crystal, lattice. So it is highly ordered. Now it is becoming disordered. Scattered, so disordered. So entropy is increased. So increase in entropy, reducing temperature drop. So chemical energy to electrical energy, there's some example, chemical energy to electrical energy. How can you get? Electromotive cell, Daniel cell, Lakeland cell, electromotive cell. Do you remember? Do you know? Battery. There what is happening? some electrical energy is produced and some chemical energy is lost. By using chemical energy, you are getting electricity, that is called battery, and that is electromotive cell. And when electricity is utilized to produce chemical energy, that is called electrical energy is utilized to produce chemical energy is called electrolysis. Opposite, electrolysis. So electrochemical reaction and electrolytic reactions. Potential energy to kinetic energy, flow of water from higher to lower. Potential energy to kinetic energy. This work done I have already calculated yesterday. So just go through, just have a look. I don't want to discuss again because this is already discussed. কাল করে দিয়েছিলাম মনে আছে দেখে নাও, জাস্ট হ্যাভ এ লুক, গো থ্রু। Reversible as well as irreversible work done. This is reversible work done. This, whenever you get the integration symbol, mind it is reversible. That is integration symbol. Why integration? Because the dp, this integral pdv, because why integral pdv? Because p is always changing, so you cannot measure until and unless you take the integration. Because p is always changing, and with that changing p, your dv is happening. Expansion of volume is happening. Continuously, you will have to change the pressure. Pressure is getting changed and volume expansion is happening. And to get the total work done, you have to take the integration. And if the pressure is constant, against the constant pressure, P2, the expansion is occurring in case of irreversible. So this is the one. It is looking like integration, but practically it is delta V, isn't it? So I end up here today. So next class I will start in that.